Okay, done. So I think we should start. Maybe just a small thing. The current the 3 talks from yesterday, they are already uploaded, both on the YouTube side, this channel, as well as on the Simon's Collaboration website. So maybe Dominique, would you start, please, the session?
Should we give it another couple of minutes?
Oh yes.
Shall I stop?
It's still 1 minute. Yes, still 1 minute. Of course, 2 minutes.
So what do we do?
Okay.
I'll leave the screen sharing on, shall I? Or
Yes,
shall
please do so.
So I guess I can do that.
Okay, should we start? So today we're pleased to have Simon Donaldson, who needs no introduction, who's going to talk about enumerative theories for structures on 4 manifolds.
Thank you. Thank you for asking me to give this talk. Hang on, where do we? Yeah, so this is based on a paper I wrote recently, Fredholm Topology and Enumerative Geometry, Reflections on Some Words of Michael Atiyah, which is to appear in the Gokova journal. So as you'll see, the paper and the talk are to some extent speculative, as we'll see. So the words in question, quotes from Atiyah nearly 40 years ago. What we have here is a non-linear way to use the index theorem. That's one. Another, you need to be careful, compactify moduli spaces. People spend their lives doing that. So you'll see the relevance of those to what we're going to talk about, I hope. So to give some sort of motivation for what we're going to discuss, in terms of this collaboration, we have ambitious goals, things we'd like to do, understand moduli spaces, for example, of special holonomy structures, and these are ambitious and many basic things we don't understand. So it's interesting to study questions which are perhaps already difficult, but where some of the foundations are in better shape, better understood. Well, that's one kind of motivation. Another one is that what we like to do and have done for since the 1980s is to study what you might call enumerative or nonlinear Fredholm theories in differential geometry, algebraic geometry, such as the very well-known cases of holomorphic curves in symplectic manifolds with almost complex structures, or gauge theory, instantons, Seiberg-Witten equations, and so forth over 4 manifolds. So the motivation is that we would like to find other examples of such theories where the same kind of ideas can be applied. So the situations we're going to consider are a bit different from those we just mentioned. We're going to consider structures living on a manifold. So we have the natural symmetry group will be the diffeomorphisms of the manifold, and so in the examples we will consider, these will be both on 4-dimensional manifolds. So one example, which is in a sense the main one, is to consider complex structures or more precisely, complex structures defining what's called a complex surface of general type. So here, as I'll try to outline, it's possible there is some sort of rigorous theory more or less on the shelf using known technology. The other kind of geometry we will consider be what are called self-dual conformal structures. So here, again, as I'll explain, there's no real prospect of a complete theory of the kind as in the first example in anything like the near future, but there are still some interesting things that one can say and observe about this about these questions in that case. So I'm going to spend a few minutes giving some background to, first of all, I want to explain, recall perhaps more what I mean by a nonlinear Fredholm theory. So what we have in mind, and this is going to be sweeping all kinds of technicalities under the carpet, is that we have some kind of nonlinear elliptic partial differential equation, which we could write schematically as S equals 0, where S is a section of an infinite dimensional vector bundle over an infinite dimensional manifold. So, the consequence of being elliptic, this means that the linearized equation is defined by a linear elliptic operator, and so working over a compact manifold, this will be Fredholm, so it has an index, an integer called mu. So formally, this index can be thought of as the difference of the dimension of the infinite dimensional manifold B and the fiber dimension of our vector bundle. So we have some sort of PDE, have a set of solutions, we'll call it Z. The other thing we want is to have some kind of mechanism which provides at least some partial compactness of this set of solutions. So at least typically it will not be compact on the nose, but can be compactified in some reasonable way. And again, we'll see examples in a moment. So this mechanism normally comes through some sort of integral identity, giving so a priori bound on some kind of energy of the solutions. So here are the very well-known, much studied examples, because the first one, as we've said, we're considering holomorphic curves in a symplectic manifold with an almost complex structure. Our space in an infinite dimensional manifold would roughly speaking be the space of all surfaces inside our symplectic manifold. Our equation would be just the equation which says that this surface is a holomorphic curve, that its tangent space is a complex subspace at each point. Then the linearized operator is, roughly speaking, the Cauchy-Riemann operator, or D-bar operator, acting on sections of the normal bundle of our curve. So this is a prototype of a elliptic operator, the Cauchy-Riemann operator over a two-dimensional manifold. Then the partial compactness arises through the control of the area of a holomorphic curve, which comes through a integral formula using the fact that we have a symplectic form, a relation between the area and the integral of the symplectic form over the curve, which is a topological invariant. Second case, we could look at Yang-Mills theory on a four-manifold and the instanton equation for an anti-self-dual connection. So here the linearized theory is expressed, in fact, in terms of a complex, because here we have to take account of the natural symmetries of the situation. So when we talked about elliptic equations, we really mean elliptic modulo the symmetries of the situation. So here our complex is given by differential forms with values in an associated bundle. I've suppressed the associated bundle in the notation. So we have the naught forms or sections of the bundle. We have the exterior derivative defined by our connection mapping to the one forms. And then we take the exterior derivative on the one forms and project to the self-dual part to get the operator D plus. And this forms what's called an elliptic complex, which means essentially that D plus is elliptic modulo the image of D. And these three objects, of course, this is the linear level, but they correspond to the basic geometric objects in the discussion, the one forms with deformations of a connection, the naught forms are infinitesimal gauge transformations, and omega 2 plus is the place where the self-dual part of our curvature lives. So it's the place where the equation is f plus equal to 0. So S in this situation would be given by f plus. And then so partial compactness arises from a well-known integral identity, which gives identity for the Yang-Mills function, the L2 norm of the curvature, in terms of the topology of the bundle you're working on. Another example, which in a sense is a bit closer to what we want to talk about, is within complex geometry, if we just consider holomorphic vector bundles over a complex surface. So the linearized theory is expressed in terms of a coupled D bar complex. So we have again, the values in a certain bundle. We have the naught forms, the 0, 1 forms, and the 0, 2 forms. So actually, in this situation, we would restrict to what are called stable bundles, and these, in fact, have Hermitian Yang-Mills connections. So in fact, we get back into the same situation as example 2. The existence of these Hermitian Yang-Mills connections gives some sort of compactness of the moduli space of solutions. So if we're in this general situation, so abstractly we have our infinite dimensional bundle over our infinite dimensional space. What we like to do in these kind of theories is to define what you can think of as an Euler class of the bundle, or perhaps we should say a Poincare dual of the Euler class, which should be a homology class in infinite dimensional space in dimension equal to the index. So we might not know completely what this homology of this infinite dimensional space is, but if we know cohomology classes, if we have some way of constructing cohomology classes, then we get numbers by pairing our homology class with the cohomology classes that we know. So the fact that we get these numbers is partly why we call one could call these enumerative theories, a way of getting numbers out of geometry. So, very broadly speaking, there are two approaches to this. In a differential geometric approach, we, if necessary, we maybe modify our equations in some way to be suitably generic. For example, if we're talking about the case of holomorphic curves with an almost complex structure, perhaps we can change the almost complex structure. If we're talking about instantons on a four manifold, perhaps we can change the Riemannian metric, or there are other kinds of perturbations we could make. So then there's a basic infinite dimensional analog of the usual sort of transversality theory, which says that for a sufficiently generic section, the zero set will be a manifold of dimension equal to the index. So provided that zero set is also compact, then we get our class zeta that we want just as the fundamental class of this manifold. And again, the same kind of arguments that one would use in ordinary differential topology show that this will be independent of the perturbation that you make. This will be, roughly speaking, a deformation invariant of the situation. So there is another important thing that comes in, that if we want to have this homology class with integer or rational coefficients, then we need to have orientations in our theory. And there is a way to discuss this using index theory for families, rather than the index of an operator, which is a number, the theory of index of a family, which gives one virtual bundles, which gives a way to discuss the question of orientability of the theory you are looking at. So many of these problems we're discussing they have a sort of differential geometric side, but also an algebraic geometric side. So in the case when something can be set up within algebraic geometry, then there's another kind of approach to define this homology class. In algebraic geometry, you don't really have the scope to make perturbations not so much scope to make perturbations as in differential geometry. So what one does is to take the set Z of your given set of solutions to your problem, and then endow that set with some extra structure which allows one to define a virtual fundamental class in the homology of the appropriate dimension. So this class will lie in the homology of your space Z, but because Z sits inside the infinite dimensional space, it also defines a class, homology class there. So there is some sophisticated general theory in algebraic geometry about which allows one to do this in suitable situations. One suitable situation is when you have what's called a perfect abstraction theory. But I don't want to give the impression that I know what that means. So I know that that's the word that people use. I have a vague idea of what it means. But let's give some simple examples of how this extra structure comes about in a sort of algebraic geometric point of view. So if we go back to the example of holomorphic bundles over a complex surface, the index mu we're talking about is in this situation with a complex, it's given by Euler characteristic of our cohomology of the complex, or more precisely, we had a real index, we need to multiply by 2, and also we take minus the Euler characteristic. So it's the Euler characteristic, of course, is the alternating sum of the dimensions of the cohomology group of the complex we were considering. We have, this is just the ordinary D-bar complex with values in our bundle. So its cohomology is just the ordinary cohomology of that bundle. So in fact, the bundle in question will be the endomorphisms of the vector bundle that you're considering. So the index we have for algebraic geometry notation would be given by this, a factor of -2, this Euler characteristic, and that's given by the Riemann-Roch formula. So in this discussion, we can suppose that the H naught is 0. So the index is just twice H1 minus H2. So if we move to complex dimensions, then the index is H1 minus H2. So what one has is, if we're studying deformations of a bundle, about a given one, then you have what's called a Kuranishi model, which says that a neighborhood in your moduli space, your space of solutions, is modeled on the zero set of a holomorphic map in finite dimensions, say F, between the cohomology groups, so F from H1 to H2. Or more precisely, we should say F is defined on some small neighborhood at the origin in H1, and a neighborhood in Z is modeled on that the zero set of F in that small neighborhood. But the point is that the extra structure encodes some of the structure of these Kuranishi maps. So one very simple, sort of familiar kind of example would be supposing H1 and H2 were both one-dimensional, the complex numbers. So that means the index is 0. And supposing our Kuranishi map was f of t is t squared, then what that's saying is that the zero set is just the origin. So we just have an isolated point in our moduli space, but we ought to count that with multiplicity 2. I mean, this is just very familiar from the way you count roots of equations in many other situations. Another kind of example, which speak closer to what we will see later in the talk, would be when the H2 has some constant dimension over our whole space, over our whole moduli space, and all the Kuranishi models are identically 0. So this is what you might call the unobstructed case. So what that means is that the moduli space, or solutions set Z, it is a manifold, but it's not. It's a manifold of the wrong dimensions, as it were. The expected dimension given by the index is mu, but Z will be a manifold of dimension mu plus nu, where nu is the dimension of the H2s. So in that case, what you do is that these H2s form a vector bundle over Z, and then the virtual fundamental class, the homology class you want, is just the Poincare dual of the Euler class of this bundle. So some of what we're saying is very general. These Kuranishi models, for example, applies very generally within complex geometry. But the situations where we can apply these ideas in the way we want are, generally speaking, quite special and tied often to low dimensions or special geometrical structures. In higher dimensions, we typically get overdetermined equations. So for example, if we look at not complex curves, but complex submanifolds of higher dimension, then the equation defining those is overdetermined. If we try to find a complex submanifold of higher dimension in our general almost complex manifold, then we won't find any at all. In terms of the deformation theories, that's reflected in the fact that one still has a deformation theory involving for example, in the case of vector bundles, we have a deformation theory involving the cohomology in the same way. But now our deformation theory is expressed in terms of H1s and H2s, but we also have higher cohomology groups, H3s, H4s, and so on. And the Riemann-Roch formula gives you a sort of topological control of the alternating sum of the dimensions of all the cohomology groups. So unless you have some good reason to know that the higher cohomology vanishes, you don't have control of the dimensions of the H1 of H2, or the difference of those dimensions. So for example, in low dimensions, if we look, say, at the simplest case, we say holomorphic bundles over projective space. Over projective spaces of dimensions 2 and 3, there's a sort of expected dimension of the moduli space of vector bundles. But if we go to higher dimensions, then there's no real, at least there's no real natural way to define the expected dimension of a moduli space of bundles. How are we doing for time? So that's part of the background. The other part of the background is some general topological ideas of things you can do when studying structures on manifolds. So imagine we have some kind of moduli space of structures on a compact manifold X, a compact oriented manifold. So by moduli space means we're studying these structures modulo diffeomorphism. And then let's suppose we're in a situation where, first of all, these structures have no symmetries. So, for example, have in mind the case where the structures are Riemannian metrics. We're considering some class of Riemannian metrics, modulo diffeomorphism, and we're in a situation where none of these Riemannian manifolds have any isometries. So then what we can do, just in a formal way, is to form a universal family, which is a bundle over our moduli space with fiber X. So that bundle has a tangent bundle along the fibers. So we get a vector bundle over our universal family. So for any characteristic class appropriate to the kind of structure we might have on this tangent bundle, we can apply that characteristic class to get a cohomology class in the total space of the universal family. Then what we can do is then to integrate that over the fibers of our fibration U maps to N. So there's a very general construction. So we have an integration over the fiber map, which maps from the cohomology, the total space of the bundle, to the cohomology of the base, but lowest degree by the dimension of the fiber. So in the end, given our characteristic class, we get a cohomology class called I of C in the cohomology of our moduli space. And then we can take cut products of these to get more classes. So in the examples we want to consider, in fact, saying we have no symmetry groups would be too strong. But if we only have finite symmetry groups, which will apply in the examples we want to consider, the same thing works provided we use rational cohomology. So the sort of very well-known case where these ideas apply is to the moduli space of Riemann surfaces. So we take n is 2, we take the moduli space of Riemann surfaces of genus some g, a number bigger than 2. That gives us these finite automorphism groups, finite symmetry groups. Our bundle is just a complex line bundle in this case. So the characteristic classes we have are the powers of the first Chern class. So we follow through this construction and we get what are called Miller-Mumford-Morita classes in the cohomology of the moduli space. And these have been studied, and there are many famous important results about these from different points of view. So, but we can do the same in higher dimensions, what we've got are sometimes called generalized Miller-Mumford-Morita. I'll write this as MMM classes, or sometimes they're called tautological classes in the literature. So that's one kind of generality about structures on manifolds. The other one has to do with the linearized theory. So we're considering some kind of structures on a manifold, modulo diffeomorphisms. So they're going to be structures satisfying an equation. So the linearized theory will look like this. In the middle, we're going to have a space like nu1, which is the infinitesimal deformations of the structures we're interested in. Say infinitesimal deformations of a Riemannian metric or something. Then we have the linearized version of our equation, which will be some linear operator D taking nu1 to some other space, nu2. On the other hand, we have to consider the diffeomorphisms in just the same way as in the gauge theory case, we had to consider the gauge transformations. So now the linearized version of that, of course, would be the vector fields, and then we will get another map given by the Lie derivative from the vector fields to nu1. So what we want to look for is the cases where this sort of thing that we have just from general nature of things makes a two-step elliptic complex like this. So crucially, we don't want to go any further. We don't want to have something which fits into a long, long elliptic complex, leading to, as we said, leading to higher cohomology. We want just something with two steps like this. So we're just halfway through. So to sum up where we are, we want to look for structures on manifolds where we have some kind of partial compactness mechanism. We want a deformation theory with a two-step elliptic complex of the kind that we've said. If we have that, we may hope to be able to define this homology class, a homology of dimension given by the relevant index, which we could then pair with these Miller-Mumford-Morita classes to get numbers. So maybe I'll pause to see if there are any questions at this point. To see no. Okay. So as I said, these things are typically rare, but there are two examples that we have in dimension 4. One is, as we said, one is just to consider complex structures. So our space is the space of almost complex structures. Our equation is that the Nijenhuis tensor vanishes. That's the equation which means that an almost complex structure is integrable. and then we're considering that modulo diffeomorphisms. Then our linearized theory is, this is very well known, this is just what Kodara and Spencer did back in the 1950s. This is just a D-bar complex with values in the tangent bundle. And the Riemann-Roch formula gives the relevant index, written as a complex index here, in complex dimensions. So this is very much like, in general, the general pattern is very much like what when we were talking about holomorphic bundles over a surface. The other one is we move into Riemannian geometry, or precisely conformal geometry, with what are called self-dual conformal structures. So just to remind you what these are, on any Riemannian manifold you have the Ricci curvature, and the sort of complementary piece is the Weil curvature, and a four manifold, or an oriented four manifold, the Weil curvature decomposes into self-dual and anti-self-dual parts. So that W plus and W minus. So W plus is a section of, you take the bundle lambda 2 plus of self-dual 2 forms, then you take the symmetric square of that, and then you take the trace-free part of the symmetric square. So writing as, so this thing, lambda 2 plus is 3-dimensional, so the trace-free part of the symmetric square is 5-dimensional. And similarly for W minus. So in fact, the Weil curvature is always conformally invariant. So this is just we're looking at the condition that the self-dual, saying W minus equals 0, is just a condition on the underlying conformal structure. So again, we get an elliptic complex. Nu 1, the space of deformations, that's just given by the symmetric 2 tensors with 0 trace on the tangent bundle. 0 trace because we're only concerned about conformal deformations. Nu 2, or V2, the space where our equation lives, that's this symmetric 2 tensors on lambda 2 minus. So that we find that this thing gives an elliptic complex, the action of the Lie derivative and the linearization of this self-dual equation make up an elliptic complex. A sort of a check on that is if you have an elliptic complex, then the alternating sum of the dimension of the ranks of the vectors involved must be 0. So you see here we have a 9-dimensional space of infinite dimensional. We have 9 functions locally defining our infinitesimal deformation. We have 5 equations, but we have 4 functions defining the vector fields, which give them, we need to divide out by. So the index is given by this funny number, a combination of the topological invariance of the four manifold, sigma is the signature, and E is the Euler characteristic. So maybe I should have said, in going back to the first case, we write C2 and the C1 squared. Those are just the notation for the Chern numbers of our complex surface. So I don't run out of time. Okay, so I said the main case we want to talk about is really the complex case, but I'm going to talk rather quickly about the self-dual case. So we have MMM classes only in dimensions modulo 4. We can start with Pontryagin class and Euler class. There is some kind of reason to hope for compactness because similar to the Yang-Mills situation, we have an identity giving a formula for the L2 norm of the Weil curvature. But in general, there isn't a very substantial theory of convergence for sequences of these self-dual structures. Okay, I'll just go a bit quickly through it. There is one example known. There are a few examples known. One of which is when we take X to be a K3 manifold, the manifold underlying a K3 surface, but take the opposite of the standard orientation with the conventions we have. But then the Yau metrics, the Calabi-Yau metrics are self-dual. We know the moduli space from the Torelli theorem. You take the Grassmannian of negative 3 planes in this space R19.3 in indefinite signature, and then you divide by a certain known discrete subgroup. Right, it's a discrete, yes, it's a discrete subgroup of the orthogonal group of this indefinite form, which is we won't take time to explain in detail.
This might not be the entire moduli space of half-conformally flat metrics, though. So these are the Einstein.
That is true. Yes, that is true. That's for a moduli space. Yes. I mean that's the point. Yeah, there could be others, but definitely we have this. Yes. So this is a case where the dimension of this is 57. You take 3 times 19 for this Grassmannian. Whereas the formula I gave before for the sort of expected dimension is 52, and the explanation is that the deformation complex has a 5-dimensional cohomology H2 given by the parallel sections of this bundle. So in this special situation, this bundle lambda 2 minus is has a flat connection. So we have this space of parallel sections which enters. So we're in the situation where we have an obstruction bundle. The dimension of the moduli space is too large, but we have an obstruction bundle, and that bundle is orientable. But from our knowledge of this group gamma, we can see that the moduli space M, we write it M3, is not orientable. So in this situation, we don't have an orientable theory. And it's an interesting problem in index theory to understand how this works in general, how the theory of orientations of these self-dual moduli spaces. So that might, anyway, we might say we should forget about that, or perhaps we have to use mod 2 cohomology or something. But there is something possibly interesting one can do, is that we can couple this self-dual theory to the instanton theory. We can consider moduli spaces of pairs of a self-dual conformal structure and a connection where A is an anti-self-dual connection with respect to the self-dual conformal structure. So in this specific example, and possibly in general, you find that the orientations cancel out, i.e. that the group gamma reverses orientations on both factors. So the combined theory is orientable in that particular example. And possibly this is something which applies in general. Well, more interestingly, we could couple the equations. So we could take the equations for a pair of a metric and a connection. We take the instanton equation for the connection, and then we can use the other part of the curvature of the connection as sort of a source term for the W minus in the way indicated. So here, in fact, to make sense of this, we need to assume that we've somehow fixed the metric in the conformal class. For example, the various ways you might think of doing that, for example, by using the Yamami metric or something. But anyway, if we have this, then you see we have a parameter. So it would seem very likely that for generic values of that parameter, the moduli spaces of the coupled equation will be a manifold of the expected dimension. So we get a parameter which is similar to the way we can deform the almost complex structure or something like that for holomorphic curves. So also the expected dimension gets a neat case. For example, if you take SU2 instantons with Chern class K in the K3 situation, the index for the coupled problem just comes being 8K minus 8. This coupled equation has some interesting features. You can exploit the Weizenblock formula on lambda 2 minus to get a sort of a bound of this form for various quantities of interest. So I think it might, mainly I'm introducing this just to show the kind of things that one can do in these theories, but in fact this coupled equation might be an interesting thing to study differential geometrically. But I want to slightly hurry over that in order to get on to the last part. So now we're talking about strictly minimal complex surfaces of general type. But roughly speaking, for a differential geometer, we could say these are complex surfaces with negative Kähler-Einstein metrics. That's not exactly correct, but it's correct enough for our purposes. So the good thing here is that there is an algebra-geometric compactification of the moduli spaces of these things. The KSBA, Kolar, Shepard-Barron, Alexeyev compactification of the moduli space. So for each, you fix the values of your Chern numbers, C2 and C1 squared, AB. For each such pair, you have some compactified moduli space, M bar AB. So now we say any pair AB, so there's actually a huge literature, the geography of surfaces, about the values of AB which occur. So, and this is the sort of picture you get, we're taking C1 squared on the vertical axis and C2 on the horizontal axis. There's sort of a region here in which the AB have to lie if you're to have one of these surfaces of general type. So this compactification is the analog in higher dimensions of something much better known, the Deligne-Mumford compactification of the moduli space of curves or Riemann surfaces. So this is probably familiar to maybe all of you, many people. But the points in the Deligne-Mumford compactification are built by you take curves or Riemann surfaces with marked points and then glue them together at those marked points to form what are called normal crossings. And then there are some conditions on, if you have a component of genus 0, you need to have at least 3 marked points for it to be allowed, for example. So this, the KSBA compactification is a similar nature. You consider surfaces with components, so that you take surfaces with divisors in them and glue these components together in what are called normal crossings. So in codimension 1, in complex codimension 1, it looks, what you're doing looks exactly like what you were doing in M bar G. But the new feature is that in codimension 2, a finite number of points, you're allowed extra singularities, and then there's a technical condition, which I won't get into, about the kind of singularities which are allowed. So it's well known that the Deligne-Mumford compactification has another hyperbolic geometry description in terms of finite volume hyperbolic metrics. And there's an analog of that, which is at least partially developed, that the points in M bar AB can be identified with certain singular Kähler-Einstein manifolds, or they might have singularities at sort of finite distance, like in the simplest case ADE singularities or something, but they might also have infinite diameter in the same sort of fashion as the Riemann surface case. So this is there's a deep theorem of Berman and Guadancia, which in this direction, but I think there's a lot of scope for understanding in more detail the geometry of these the geometry of these metrics in the compactification. So anyway, the proposal, we call this, is for each relevant AB, to define a virtual fundamental class. Then we compare it with the relevant MMM classes to get numbers. What are the MMM classes? We can take C1, we can take powers of C1 and C2, and then perform our construction to get the class sigma PQ, and then we can take products of those. So what we get is a ring with an infinite number of generators, the generators given by the sigma PQ, and every element of that ring can be paired with our fundamental class, assuming things go the way we want. So this is a huge ring. So we would get a huge collection of numbers if we did. But maybe we don't. Maybe that's too ambitious. Maybe only some of these are well defined or could be calculated. But for example, if we take C1 cubed, and apply a construction to that, that gives us a two-dimensional class on the moduli space. And this is particularly interesting because it's the first Chern class of the natural ample line bundle on the moduli space. So we might be less ambitious and just restrict to powers of that thing. So there is I think a definite algebraic geometry question you can ask is whether there's a perfect obstruction theory on these in this KSBA theory. So that's something I'm completely unqualified to comment on, but I know there's some work of Yunfeng Zhang in that direction. People, it's an interesting question. But we can also imagine at least attacking these questions differential geometrically, because at least schematically, it's very much like things that we like to do when studying the boundary of moduli spaces of G2 manifolds in terms of various kinds of singularity formation or splitting up into twisted connected sums and so forth. So it's certainly conceivable that we could have extend our routine deformation theory over the whole compactified moduli space in a differential geometric fashion. So whatever the outcome, I think it's interesting in other situations, for example, in it's called the DT theory, there's interest in trying to understand the relation between differential geometric and algebraic geometric approaches. So if there is some fundamental difficulty in producing a perfect obstruction theory or whatever, then it will be interesting to understand that in connection with these more general questions. So I want to emphasize that we don't have this theory. This is the proposal. And there are certainly criticisms that one could make of this whole project. Well, first is that we don't have a theorem. The foundations are shaky. The second is, even if we had the foundations, it would look nigh on impossible to do any calculations. I mean, there'd be probably almost no examples where you could calculate any of these numbers for various reasons. One being that there are very few cases where there's a complete description of the moduli spaces of these surfaces. And even where there is, even fewer cases where there's a complete description of the compactification and so forth. And finally, maybe most important, you might say, even if you had the foundations, you did some calculations, what would that give you? What is the point of having these numbers? It's not quite clear what these things would mean compared to the situation in, say, Gromov-Witten theory or something where you will produce invariants of symplectic manifolds. But on the other hand, these things could possibly connect with other ideas and be important. Certainly the analogous constructions in the Riemann surface case, where we evaluate these Miller-Mumford-Morita classes on the compactified moduli space, are very important and have connections with all kinds of things. So another strange feature is, so many surfaces of interest lie in moduli spaces of negative dimension. So where our whole discussion collapses. So if we go back to this picture, if you look at remember the formula for the virtual dimension would give a region like this, where the virtual dimension is positive. All of these surfaces up here live in negative dimensional moduli spaces. And even when the virtual dimension is positive, often it has no relation to the dimension of the actual moduli space. The moduli spaces typically have much larger dimension. So even if you take a surface in CP3 of degree D, at least 6, then you find that the two-dimensional cohomology of the tangent bundle is isomorphic to this thing. So there's an excess dimension given by this formula here. There are also many examples where your moduli space for a fixed AB has many components, all of which have different dimensions. So anyway, so I've got 5 more minutes. So what we're going to do is to partly answer the criticism about examples. We're going to work out an example, but we're going to impose symmetry to make things easier. So we'll just go through this quickly. So we take coordinates x1, y1, x2, y2 on P3, and we're going to consider the family of surfaces of degree 6 invariant under a certain finite group, which it's written down here. So you see we're allowed to multiply by 6th roots of unity in a certain way, and then we interchange x1, y1 and x2, y2, so a certain group. And it's elementary to find all the surfaces are invariant under that, served by that group. And if we leave out some obviously bad ones, we get just a two-dimensional family with the coefficients a and b. So here h plus and minus stand for these two quadratic expressions. So imposing the invariance under this group, we can cut down our huge moduli space of sextics to this small tractable moduli space. So the recipe I said tells you that the H2 for your sextics is given by lambda 2 of C4. If we look at the G invariant part of that, this is just one-dimensional, spanned by this form. See that? If you look at the way the group was constructed, it's precisely something that will preserve this form, essentially. So although we have a two-dimensional moduli space, the virtual dimension is 1, the complex dimension is 1. So there are two numbers we should be able to compute, which are the pairings of the virtual fundamental class with these two MMM classes. Okay, so I have 2 minutes. So a naive thing we can do, which is just to take our space of surfaces given by these parameters A, B, the naive compactification would be to take CP2, we add a line at infinity. So that would just correspond to taking the points at infinity would correspond to algebraic cycles. We would take unions of quadrics in the pencil generated by two expressions, possibly with multiplicities. So these quadrics all meet in a sort of configuration of lines, 4 lines. So but this is not the KSBA compactification, which is different. So the easiest part I said, supposing we just consider this family here. So we look at where b equals 0. We take a goes to infinity. So the naive limit would be to say, when a is infinity, or we take it across the other side, we just get h plus cubed equals 0. We should take the quadric given by h plus equals 0 with multiplicity 3. But it's quite well known from, I think, but that's not what you should do. What you should take is the a triple branch cover of this quadric as the natural limit of this family, where the branch curve is the intersection of the quadric with the sextic defined by the rest of the first 4 terms. So I'll slightly go, I finished up to my time, so I'm going to slightly hurry on. So what you get is you get a different compactification, the KSBA compactification, and these we can describe these. It's convenient that these are both toric manifolds, so they can we can describe in a sort of toric fashion. So the first one, essentially CP2, that's familiar. This is the toric picture of CP2, but the KSBA one is different. It looks like this toric variety. In fact, it's an orbifold, so it's toric orbifold. So there are, in fact, there's a whole, yeah, so this is, I should finish now, time's up. So this was the line we were considering where B was 0. So this point 3 is that triple branch cover we were saying. And then we get a whole, along this edge of this part of the toric variety, we get a whole family of triple branch covers. And there's a similar discussion here when if you let a equals 0 and you let b to infinity, then you get more or less a double branch cover, and then you get a whole family of double branch covers, and then these come together at this most singular point, which is sort of a degeneration both of the triple covers and double covers. But I'm out of time to explain all that. But anyway, once you've described this moduli space, you can go ahead and do the calculations. You have this, once you have to work out the Euler class of this bundle of H2s over it. This moduli space has 2-dimensional cohomology you have to calculate in. And in the end, you get 2 numbers. So, so it's kind of a proof of principle that at least when you simplify the situation by imposing these symmetries, one does get problems which one can just write everything down, construct moduli spaces, and do these kind of calculations. Okay, so I'm sorry, I'm slightly over time. So that's the end of the talk.
Thank you. So let's thank Simon. Do we have any questions? I had one. So there are situations such as the Tian-Todorov theorem for deforming Claviers or whatever, when there are obstruction theories which are, there are obstructions which are automatically ineffective. Is there any kind of reason, geometric reason, why so many of these examples seem to have obstruction bundles which don't obstruct?
Yeah, well, I have some sort of partial. I have some sort of partial answers, which are somewhat discussed in the paper, but it perhaps take a bit long to try to explain. Maybe say there's an analogous thing, which is if you look at the holomorphic curve theory on an algebraic surface, then it all goes wrong in the sense that most curves live in spaces of the wrong dimensions, because curves are also described as divisors. So the sort of Gromov-Witten theory doesn't see that. So that's why, for example, when you take the Seiberg-Witten invariance and the correspondence with Towns's work, only a very few curves on a complex surface contribute to those invariants. So at least in some situations, the fact that you get the wrong dimension moduli spaces is connected to the fact that curves on surfaces live in wrong dimensional moduli spaces. That's not really that's more of an analogy than an actual mechanism for curves, but there are, yeah. But it would be very interesting to understand that point. Yeah.
Okay, so I think Jason and then Claude have questions.
Yeah, my question was maybe it's more on a very specific point. So I noticed when you were describing the expected dimensions of this coupled system that you had on the K3 surface with the metric and ASD instanton, that you got this number 8K minus 8 for the dimension of the moduli space. Is there some kind of quaternionic structure on this moduli space that sort of reflects this fact it's a multiple of 8?
That would be exciting. I don't know. Yeah, that the fact that you get this 8 coming out is one reason why it seemed like a good thing to be doing, or a hint that it might be a good thing to be doing, because your cohomology classes live in dimensions 0 mod 4, so it's good to have moduli spaces that are dimensions 1 by 4. But I don't know any. I don't know much more than what I told you about those equations. That'd be very interesting to understand if there was such a thing.
Great, thanks.
Claude, do you have a question?
Yes, another interesting case where you do have obstructions is actually something you discussed briefly but passed over. Namely, if you look at anti-self-dual structures, anti-self-dual conformal structures on K3, then the H2 is always non-zero, and actually if you calculate the expected dimension of the moduli space, it's therefore off from the actual dimension of the moduli space of the self-dual anti-self-dual structures that arise from Calabi-Yao's. So I wondered if there's an interesting cohomology class that arises here, and so that might be a very nice place to try to put these ideas into effect. There's a simpler case I've been sort of thinking about where the dimension of the moduli space coming from algebraic geometry is not what you would expect. If you look at a surface of general type, and if you look at curves that are in the canonical class, then the number of sections of the canonical line bundle is a topological invariant. It's related. It's a geometric genus. It's related to the value of B plus. But on the other hand, in Taubes's approach to symplectic form manifolds, you get actually kind of for generic perturbation, you find that there's only one canonical pseudo-holomorphic curve that you would expect to get. The deformation theory has index 0 there, but in the concrete world of algebraic geometry, you don't get just one canonical curve, you get an entire family, depending upon the topology of the four manifold. I think this is probably an easier case to try to give some concrete meaning to, but in terms of saying, well, on this space of basically a projective space of sections of the canonical line bundle, there's a certain class. But
well, yes, it's related to what I was saying to Dominic. But I mean, there would be an abstraction bundle point of view. I mean, you would have a bundle over this projective space, and you work out its Euler class, and you want to get. I think that would be part of. Yeah. Well. Yes. So that. I think that's probably sort of known that how that works. But of course, because you have singular curves, there's some
right.
But in the
one of the fascinating things about that particular example is that the normal bundle of these curves is actually a spin bundle, and so the fact that it has index 0 is related to the fact that there's, when you look at the index of the Dirac operator in real dimension 2, it's always 0.
Mm-hmm. Right. Right.
Okay. If there are no more questions, I suggest that we thank Simon again, and then we move on to the discussion on